Hello, good morning and warm welcome dear students to your geography class. Let us now continue our chapter number 5, Ocean Currents part 3. Now today's lesson is going to be very exciting. This part is going to be very exciting. You are going to love it. In the second part of the lesson, you learnt about horizontal surface ocean current, continental structure, effects of ocean currents on human life. You have learned about this, right? I hope you all remember. It was very nice. And today you will see something new and exciting. You will see an experiment on how waters mix, means the hot water, cold water, the warm current, cold current, how do they mix and how do they move along the earth. And you also see the importance of ocean currents, how they affect the climate and the plantation in the region. Or you will see the live examples also. So let's dive in. Now in this third part of the explanation, you will learn about circulation of waters in the deep ocean, importance of deep ocean currents in the movement of seawater.
Welcome to the Abyss. I'm Jacqueline, and today we are discussing deep ocean circulation, the final part in our ocean circulation series. Let's dive in. The last component of ocean circulation is the circulation that occurs in the deep ocean. On average, the ocean is 4,000 meters deep, whereas the wind only affects to about 1,000 meters. This means that the currents of the deep ocean are density driven instead of driven by the wind. This circulation is referred to as the thermohaline circulation. Thermo comes from the Greek word for heat, and haline refers to salt. Therefore, the circulation in the deep ocean is caused by the varying temperatures and salinities of the water and how these two properties affect its density. Similar to air masses, which have temperature and humidity signatures, water masses have temperature and salinity signatures. This means that temperature and salinity can be used to identify and to follow water masses as they circulate. The density of water masses can also be used to determine what will happen when two water masses meet. For example, when a denser water mass encounters a less dense one, it will sink and move beneath it. The effect of temperature on the density and movement of water can be demonstrated by water in a tank. We start by placing ice cubes in the water and adding a few drops of food coloring so we can see the water's movement. The ice cools the surrounding water and the water becomes denser, causing it to sink. Once it has sunk to the bottom, it spreads outwards.
These are the cold
We
currents.
can also demonstrate the effect that salinity has on the density of water. We're going to start by pouring salt into water, mixing it up and adding a few drops of food coloring. This creates a water mass that has a high salinity compared to the water in our tank. When we pour this water into the tank, since it has a high salinity, it has a higher density. Therefore, the water sinks to the bottom and then spreads out. In the Atlantic, salty surface water cools in the Arctic and sinks. This forms a deep water mass called the North Atlantic deep water. A similar water mass forms in the Antarctic and is called the Antarctic bottom water. This mass gets its name because it is the densest of the water masses and consequently moves along the bottom of the ocean. Therefore, when the North Atlantic deep water encounters the Antarctic bottom water, It moves over the top of the bottom water since it is less dense. Similar deep water masses to the ones found in the Atlantic are not found in the North Pacific. This is because the water at higher latitudes is too shallow and not saline enough for deep water masses to form. One water mass that has a unique temperature and salinity signature is the Mediterranean Sea mass. Since the Mediterranean Sea receives so little precipitation and has such a high rate of evaporation, the water mass that forms there has a high temperature and a high salinity. Eventually, this water mass becomes dense enough that it sinks and flows into the Atlantic Ocean. Although the Mediterranean Sea mass is much warmer than the surrounding Atlantic water, it stays relatively deep because it has a much higher salinity. The movement of these water masses forms an ocean-wide circulation pattern referred to as the Great Ocean Conveyor Belt. The ocean conveyor belt starts with water being cooled off the coast of Iceland due to cold air from the Arctic. This water then sinks to the bottom of the ocean and flows south, forming the North Atlantic deep water. This water has a high salinity but a low amount of dissolved nutrients. The water then moves south towards Antarctica, where it meets and moves over top of the Antarctic bottom water. These two water masses then move farther south, where they join a fast-moving eastward current around the edge of Antarctica. This current efficiently mixes the North Atlantic deep water with the other water masses. From this current that moves east around Antarctica, two sections break off. One moves into the Indian Ocean and the other into the North Pacific. As these sections move north, the water warms and rises, eventually upwelling. This upwelling brings dissolved nutrients from the bottom of the ocean into the surface waters. This makes these areas of the ocean very nutrient-rich. The warm surface waters then circulate back around the globe, eventually returning to the North Atlantic where the conveyor belt begins. Unlike the surface ocean currents, the deep ocean currents move incredibly slowly. It can take these water masses decades to centuries to move across a single ocean basin. The ocean conveyor belt describes the general pattern of the circulation, but this does not mean an individual water molecule will follow its exact path. However, studying the circulation of the deep ocean is incredibly important. That's because it has a huge impact on our climate and the deep water transport of dissolved nutrients. So that is how the thermohaline circulation and the deep ocean currents work. That concludes our series on ocean circulation. If you liked this series and would like to see a series on another topic, let us know in the comments down below. Thanks for watching, and until next time, I will see you later.
Now we have finished that part, and now we will continue to the final part of this lesson is we will learn about how ocean currents affect climate and plantation in a region. You will see live examples of how it affects.
Hello and welcome. In this video, we are going to examine how ocean currents affect the climate of coastlines they flow past. Before we get into that, let's just remind ourselves about the definition of climate, as well as the factors that affect global climate. Climate is best defined as the general atmospheric conditions over a place over a minimum of 30 years or more. The 5 factors that affect climate are latitude, or distance from the equator, ocean currents, which we are going to examine in this video, distance from the ocean, or continentality, altitude, also known as height above sea level, and relief, or the shape of the land. Ocean currents are giant underwater rivers or conveyor belts of water that flow in the oceans. There are many contributing factors that create these ocean currents. Some of these include the winds, Earth's rotation, the temperature of the water, and the salinity or the salt content of the water. There are two categories of ocean currents: warm currents and cold currents. This map of the major global ocean currents shows something quite important that we should take note of. Warm ocean currents originate at the equator and transport warm water south and north to the high latitude, and cold ocean currents originate at the high latitudes and transport cold water towards the equator. From this map, you can also identify some global climate patterns created by ocean currents. Almost all coastlines where major cold currents flow are dominated by a light brown color that on this map indicates a lack of vegetation. These regions are deserts. Let's look at the effects of ocean currents by examining the effect they create on the coastlines of countries or regions. A perfect example to use here is the Southern African region. Situated to Southern Africa's east coast is the Indian Ocean, and along the west coast you can find the South Atlantic Ocean. Both of these oceans have a massive impact on the climate of Southern Africa. The current flowing through the section of the Indian Ocean that borders Southern Africa is the warm Agulhas current. This current moderates the east coast temperatures as it provides a constant flow of warm water from the equator, which leads to lots of evaporation occurring off this current. As a result of this, places along the east coast like Durban have humid summers with lots of rainfall. As you can see from these pictures, Southern Africa's east coast also has a lot of green vegetation. This picture shows the Kranskloof Nature Reserve, and you can see the densely packed trees and greenery everywhere. George, which is another town along the east coast, is well known for its beautiful green scenery, which it can also attribute to the warm Agulhas current. The current flowing in the South Atlantic Ocean is the cold Benguela current. This current brings cold water from the South Pole, and due to the cold temperatures of the water, very little evaporation occurs along this coastline, and the climate is extremely dry throughout the entire year. The west coast of Southern Africa is dominated by the Namib Desert, which is widely thought to be the oldest desert in the world. Estimates put its age at around 55 million years old. It is also one of the driest deserts in the world, and very few people inhabit it. While the scenery of the Namib lacks the greenery and vegetation, that doesn't make it any less magnificent to look at. The west coast of South America is also dominated by a desert called the Atacama Desert. The west coast of North America contains the Sonoran Desert, and the west coast of Australia sees the early parts of Australia's outback, which is a large series of interconnected deserts. Before we finish the video, let's just summarize what we have learned. Ocean currents are giant underwater rivers that flow in the oceans. There are two different types of ocean currents, warm and cold. Warm currents raise average coastal temperatures and make these coasts more humid with more rain, especially in the summer. And finally, cold ocean currents lower the average coastal temperatures, making them extremely dry in the process. Deserts often form along these coasts. And that's all for this video. Thank you for watching. I hope you found the content educational and entertaining.
So students, you have understood this part and you have seen all the live examples, also how climate affects the region. Some regions get rainfall good, so the plants growing there, and other region where the cold currents are coming in, there is no proper rainfall, and so there is all desert over there. The land does not get good water over there. You have learnt a lot in this lesson. I hope you have understood very well, students. Now we will be doing an assignment which you will be seeing in your classroom. It's a very nice assignment and is very important for you. So do it. Thank you.